Hi everyone. Let's learn how to detect where a given function is increasing and where it is decreasing by using its graph and by using its formula. Let's start with a graph. In the first exercise, we must identify the intervals on which f is increasing and on which f is decreasing by looking at the graph of the function. If you would like to try this exercise on your own first, stop the video now. You can also download these notes using the link in the video description. The function is increasing where the values of the function go up as you look at the graph from left to right. For example, right here the function is increasing because as I look at it from left to right, the values of the function are getting larger and larger. This piece of this graph is produced by the inputs between -2 and 0, which means that on the interval from -2 to 0, the function is increasing. There is one more place where this function is increasing. It is right here on the interval from 1 to 2. There are 3 places where this function is decreasing. This function is decreasing here, this function is decreasing here, and this function is decreasing here. The associated intervals are the interval from -infinity to -2. I'm assuming here that the function continues its behavior this way. Then the second place is from 0 to 1. And the final interval is from 2 to 5. There are 2 remarks I want to make before we move on. First, note that a positive derivative tends to happen when the function is increasing, and the negative derivative tends to be associated with places where the function is decreasing. In the first piece of the graph, the function was decreasing and the derivative there is negative. The slope of this line is negative. Second piece, the derivative is positive, function is increasing. Third piece, the derivative is negative because the slopes of the tangent lines are negative and the function is decreasing. Then the function was increasing and the slopes of the tangent lines were positive. The derivative was positive. The second thing I want you to notice is that this function changes from increasing to decreasing and vice versa at critical numbers. For example, -2 is a critical number because the derivative doesn't exist there. We have a corner, meaning this function is not differentiable at -2, and the function changes from decreasing to increasing there. At x equal to 0, another critical number, the derivative doesn't exist, and the function changes from increasing to decreasing there. Let's try one more. 1 is a critical number because the derivative there is 0, and the function changes from decreasing to increasing there. One more thing you should notice is that not all critical numbers will produce a change from increasing to decreasing or vice versa. For example, x equal to 3 is a critical number because the graph of the function has a corner, meaning the derivative does not exist there. Yet, the function goes from decreasing to decreasing. Critical numbers are just candidates for places where the function can change from increasing to decreasing and vice versa. These 2 remarks are exactly what's written at the bottom of your notes. The first observation says that a continuous function can, but does not have to, change from increasing to decreasing or from decreasing to increasing at critical numbers. The second observation is a theorem we proved in the previous video about the mean value theorem. The theorem says that if the derivative is positive on an interval, then the function is increasing on that interval. And if the derivative is negative on an interval, then the function is decreasing on that interval. Let's see if we can use this observation and this theorem to determine where a given function is increasing and decreasing without seeing its graph. In this problem, we must find all the intervals where this function is increasing and all the intervals where this function is decreasing. If you would like to try this problem on your own first, stop the video now. We know that the function can change from increasing to decreasing and vice versa at critical numbers. Let me find critical numbers of this function. To find critical numbers, I take the derivative, and I get 3x squared minus 6x minus 9. Then I ask myself two questions. Are there any x's that make this derivative not defined? And are there any x's that make this derivative 0? This derivative is a polynomial, meaning it's defined everywhere. The first condition gives us no critical numbers. To determine what x's make this derivative equal to 0, let me first factor 3 from each term of the derivative, and I will get 3x squared minus 2x minus 3 equals 0. Let me factor this even further. I get 3x minus 3x plus 1 equals 0. This suggests that I have two x's that make this derivative 0, x equal to 3 and x equal to 1. To visualize these critical numbers, let me draw the x-axis and add those numbers onto the x-axis. I will have -1 on it and I will have 3 on it. I make sure to write the smaller number on the left and the larger number on the right. I know that my function can change from increasing to decreasing where these critical numbers are. So now I need to determine between -1 and 3, is the function increasing or is the function decreasing there? Between -∞ and -1, is the function increasing there or is the function decreasing there? Let me show you two methods of doing it. Method 1 is the following. Your goal is to determine what happens from -∞ to -1, what happens between -1 and 3, and what happens between 3 and infinity. What's more, you want to know what happens there to the derivative, because you know that if the derivative there is positive, the function will be increasing, and if the derivative there will be negative, the function will be decreasing. So my goal is to determine, is the derivative there positive or negative? To do that, I will need a test point from each interval. Any point in that interval. For example, a point in this interval is -2. A point in this interval is 0. And finally, a point in the last interval is 4. You can choose other test points if you wish, as long as they're inside of those intervals. I will test now if my derivative is positive or negative at those test points. For example, when I plug in -2 to my derivative, you can plug it in right here, or you can plug it in right there. This is the same thing. When I plug in -2 to this expression, will I get a positive number or negative number? Let's give it a try. When I plug in -2 here, I will get -5. That's a negative number. I plug in -2 here, I get -1. That's also a negative number. These two numbers will be negative. When I multiply them, I get a positive number. Multiplying it by 3, I get a positive number. So that means when I plug in -2, the derivative is positive there. What happens when I plug in 0? When I plug in 0 to my derivative, let me plug it to this function this time, or this formula, this is the same function. I get 0, 0, and -9, and I get negative number. In the last interval, the interval from 3 to infinity, we chose the test point 4. When we plug in 4 to the derivative, we will get 3 times 4 minus 3, which is a positive number, 4 plus 1, which is a positive number. All those numbers will be positive, the derivative will be positive. This means that on the first interval, the derivative is positive. Second interval, the derivative is negative. Third interval, the derivative is positive. Positive derivative on an interval means that the function is increasing on that interval. Negative derivative of an interval means the function is decreasing. Positive on the last interval means that the function is increasing there. I told you I was going to show you two methods. So here is method number 2 of reaching the same conclusion. Method number 2 says, draw the derivative instead of drawing the table. If you were going to draw the derivative, you would start with the x and y axes. Then you know that the derivative has 0 places, 3 and -1, which means your graph will go through -1 and 3. What's more, you know that the graph of a second-degree polynomial is a parabola. What's more, that parabola will be opening up because the sign in front of x squared is positive, which means that the graph of the derivative looks something like the following. This is the derivative. By looking at this graph, can you tell me where this graph is positive? This derivative, this function is positive between -∞ and -1, and it is positive between 3 and an infinity, which is exactly the same conclusion we obtained when we used the table. The derivative is negative, it is below the x-axis whenever this graph is below the x-axis, which means x's are from -1 to 3. So for x's between -1 and 3, the derivative is negative, and we obtain the same conclusion. Let's write down the final answer. We were supposed to find the intervals of increase and decrease, and we realized that the function is increasing on the interval from the -∞ to -1, and on the interval from 3 to infinity. And this function was decreasing on the interval between -1 and 3. This is our final answer.